Okay. The topic for today's lecture is called K nearest neighbors. How many of us have heard this quotation that you are the mean of the 5 people you most talk to? You're the average of the 5 people you most talk to. What does that mean? That if I have to estimate your behavior or predict your behavior for some unknown task which I don't know, I can perhaps pick up your 5 best friends, closest friends. I can understand that what their behavior is and then just take an average of those. Right. Today's topic, K nearest neighbor, is fairly similar to this topic. So, without going into the specifics of this method, where do you think you may want to look for methods or predictions which are similar to some existing methods or predictions? How many of you say that I like this particular song on Spotify? Can you recommend me some other song? So that notion of similarity, which we also discussed in movie recommendation, is what you can also use. You can also then leverage methods like K nearest neighbors. You have to have some vector which represents your likeness for certain kinds of songs, and then for that vector we are trying to find out similar songs. Similarly for movies. So we'll be looking at K nearest neighbors for 2 classes of problems today, classification as well as regression. Let's take a very simple example. We have the classification problem between oranges and apples. We'll say that we have only 2 feature attributes, the amount of red color on some scale and the radius of the fruit. And I ask you this question, that for the question mark shown on the screen, what fruit is it? What is your answer? Orange. Why? In this 2-dimensional feature space, which we believe is a good feature space for classifying these 2 categories of fruits, this question mark is very close to multiple oranges. It's very far from apples in this 2-dimensional feature space. Right? So we have already now studied K nearest neighbor classification, if we see this. Okay, so Deep is asking a question about constructing a decision boundary. We will come to this in about 10-15 minutes, where we'll study the topic of parametric versus non-parametric methods, and there you'll be able to appreciate why we are looking at the nearest neighbors only at this point of time, and not looking at an approach which creates, let's say, a hyperplane to separate out the 2 classes. So it's most likely an orange because it's similar to orange in the feature attributes, in the 2-dimensional feature attributes given to us. We start with the attendance. Okay. In the regression case, I will take this example of house price prediction. So I have area and age as 2 attributes. Does this graph have any other attribute? Does this graph show you 2 attributes or more than 2 attributes? Yes. What is the 3rd attribute? Probably the size, which I am representing by the radius of the circle. So there are these homes which are, okay, the area was already captured. I don't know why I created a bigger, oh sorry, this is showing the price. The circle's radius is showing the price. So 2-dimensional input and 1-dimensional output. Instead of writing the number, I am drawing a bigger circle to represent higher price. Why is this home expensive? Higher area and it's a new home. Whereas this home has a small area and it's a very old home, right? So it's a very simple model. So therefore, if we were to pick this particular question mark home, we'd expect it to be expensive because the area is high, the age is not too old. And we see similar homes which are large in area and not very old. To understand how nearest neighbors work, we will look at an extreme simple example called one nearest neighbor, where our prediction would be based on just one close neighbor. So we create something known as a Voronoi diagram. We have 2 input points in a 2D space, feature 1 and feature 2. You create a line joining these 2 points. Then you take the midpoint of this line and you draw a line perpendicular to the line joining these 2 points. Why have I done this exercise? It looks like a decision boundary for only these 2 points. If you are on this side of this line, then your predictions would be red or blue? Red. Why? Because every point on this side of the line is closer in the Euclidean space, in the feature space, to the red point in comparison to the blue point. Similarly, if you look on the other side of this line, every point would be closer to the blue point. Therefore, its prediction would be blue. Therefore, if we were to make a classification, a binary classification, we would say that everything on this side would be predicted red, everything on this side would be predicted blue. Okay. Why don't you make a rough diagram like this in your notebook and try and create the Voronoi diagram? Now you have multiple points. So I won't tell you the answer, I'll let you try the approach here. Doesn't need to be exact, something approximate to this. But the important concept is how do you handle multiple points? At least the first step I want everyone to do, which is start with the last 2 points, P1 and P4, and do exactly what I did 2 minutes back. Join the 2 points, find the midpoint, and draw a perpendicular line. Keep drawing the perpendicular line. At one stage, you'll realize that something is wrong. And feel free to discuss with your neighbors. Okay, I'll give another hint. Start with P1, P4, join the points, find the midpoint, draw a perpendicular line. Do the same starting from P2 and P6 and draw those lines. Something will happen if you keep extending those lines. I think, so the question is, would you see any differences if you consider the L1 norm versus L2 norm? So typically these things are done in the L2 norm space. Yeah. I'm not sure. I don't see a reason why there should be anything different, apart from the lines being slightly different. All right. So we start with P1 and P4. We draw a line joining these 2 points. We find out the midpoint. Let that midpoint be A. And I draw a perpendicular line. I keep extending that line till a point B on the left hand side. But point B is closer to P3 than it is to P1. So therefore now the closest point, the closest red point to this line is P3 and the closest blue point is P4. We will do the procedure now between P3 and P4. Because this point is no longer the closest neighbor. P1 is no longer the closest neighbor to a point B. P3 is the closest neighbor. We draw the line between P3 and P4. We find out the midpoint. We extend it further. And if you keep doing this further, you will get a surface like this, a decision boundary like this, which separates out the 2 classes. It's not very well drawn, especially between P3 and P5, but I hope you get the point. How do you decide where to stop the perpendicular? Would be, you decide that by looking at the distances between the other points, other pairs of points, other red points, other blue points, wherever the distance. So this is a very ad hoc, very naive implementation which I am telling. Here we observed that the point we kept on extending, and every point that you were considering, now you have to consider the pairwise distances between that point and P1 and P3 and P2. It turns out that P3 is now closer to that point than P1. So therefore we need to shift. If we extend, I'm not able to fully understand. If we extend B further in that direction, then to P5, yes, that will happen. So if this keeps happening, we will extend it further, but we'll have to consider the first point where the first pair where the difference starts occurring. Right? So this is one way to do this, where you construct these lines. The other is to do it via a grid. Right? So I think the grid method is what all of you will perhaps find it easier. You look at every point. In fact, in the screen also you can see some grid points. Right? You look at every grid point and you find out the closest pair of points, the closest blue point and the closest red point, and you see which of them is closer, the blue or the red one. And whichever is closer is the color that you assign to that dot. Does it make sense? That's an easier way to consider. Can you repeat? Yeah. Yes. But we do it between the closest pair of points. So importantly, we saw that between any 2 pair of points, the decision boundary was linear. So therefore, even though this does not look like a linear decision boundary between the 2 classes, this is a piecewise linear boundary. And if you extend this to a more sophisticated example, if we look at an outer circle and an inner circle, if we were to apply one nearest neighbor, we will get a decision boundary which is itself a circle, but it is not exactly a circle, it is piecewise linear. Right? It will be jagged lines like you would create in a logo-like language, but it will appear, if there is enough of them, it will look like a circle, but it's actually piecewise linear. Okay, so we will, I wanted to take this diagram and show me draw the colors corresponding to the blue class region and the red class region with k equal to 1. Can you draw this in your notebooks? Approximately, you don't need to be exactly correct. Some region in this graph, in this Cartesian space would be blue, some would be red for k equal to 1. If you've done k equal to 1, draw for k equal to 3. Okay, does your boundary look like the one which I've drawn on the screen? You look at, so I told you the easier method, you look at every point on this grid, you consider is a red point closer or is a blue point closer, and you assign the color according to that. Okay, how about k equal to 3? K equal to 3 means that now your prediction would be the class, you'll consider 3 closest neighbors to a test point, and the majority class amongst the 3 closest neighbors would be what you would predict. For example, if we were to pick up a point, if we had a test point which is this black dot, if we consider its 3 closest neighbors, the majority of them are blue. So therefore, the prediction for this test point would be blue. So based on this, can you now draw the classification boundary or the prediction set? The blue color region and the red color region with k equal to 3 nearest neighbors. At every test point, you consider the closest 3 points and you take the majority vote and then you assign the label. Okay, Shatakshi has a question. Okay, so I would suggest that for now you just consider the simple variant where you consider the grid and you just consider the closest possible point, which could be either be a red point or a blue point, and whichever that point is, my prediction for that test point is that particular class. Okay, how does the decision boundary look like for k equal to 3? It looks perhaps smoother, it looks like what we would have wanted. Okay. So if we've gone from k equal to 1 to k equal to 3, what do you think is happening in terms of the bias variance trade-off? If for k equal to 1, what do you expect? Higher bias, higher variance? High variance. So this is where KNN people mostly get this question wrong if I ask in the exams. If you ask decision tree, what does more number of depth, does more depth have more variance? Neural network and for linear regression basis functions, more degree has more variance. K nearest neighbor, less number of neighbors has higher variance. Right? So people typically, if you don't understand the concept, you don't draw such mental pictures, you may get it wrong. K equal to 1 will have higher variance. We'll discuss it in more detail later. K equal to 3, you are observing that the model is getting more averaged out, which is meaning that it is getting you more bias. Okay. We can do the same thing for regression. You are given these values x1, y1, x2, y2, x3, y3, and I have shown you a linear regression plot. Can you make a one nearest neighbor regression plot? You have to take the learning from the classification point example and see how would you extend it to regression. The idea remains the same. Your prediction is based on the k nearest neighbors. In the case of classification, you were doing the majority vote. In the case of regression, you will do the average of the k nearest neighbors. But for one nearest neighbor, you don't need anything sophisticated. Okay, do we have an answer? For x less than x1, all the points, all the test points, the closest training point is x1. So therefore, for x less than x1, your one nearest neighbor's prediction would be just the value corresponding to x1, which is y1. Right? So all the points x less than x1, the nearest neighbor point is x1 comma y1. Right? For points which are between x1 and x2, we can say that if x is less than x1 plus x2 by 2, still the closest input point is x1. Corresponding to that, your prediction is still y1. If you move beyond x1 plus x2 by 2 till x2 plus x3 divided by 2, your prediction would be y2. And beyond x2 plus x3 divided by 2, your prediction would be y3. Right? So you are getting these levels, different levels of values. What would be your prediction for x tending to infinity? y3. For x tending to minus infinity? y1. So if you know that the data indeed has linear relationships and you're trying to extrapolate beyond the region, you will have very poor predictions because your predictions would be just based on the closest data points that you have. If you knew that the data was indeed linear, which we often don't know. Okay, so now we come on to the most interesting part of today's discussion, the most confused part of today's discussion, parametric versus non-parametric. What do you understand when you first hear the term non-parametric or parametric, let's say? What do you understand when you hear parametric? Tunable, okay. Something which will influence your models. The other places where you hear parameters is functions. In Python, you pass parameters, etc. Where else? What else comes to your mind when you hear about parameters? Parametric, neural network, linear regression, theta parameters, etc. Sorry? Hyperparameters, okay. What do you think non-parametric might mean? Okay, other answers? Non-parametric. There are no parameters? You can't learn the parameters? Okay. So good that we have a lot of confusion in this classroom for this question, because if you look at the answers, if you look at the definitions in various textbooks, you will see that there is a bit of confusion about the exact definitions of non-parametric versus parametric. We'll take one such example, after which we'll take 2-3 different answers and different ways to understand parametric, non-parametric. Let's consider a linear model for classification. What is the linear classification method that we already know? Logistic regression, which produces the linear decision boundary. So the decision boundary would be like y equal to mx plus c. Right? The number of parameters in that would be 2, m and c. If we do k nearest neighbors, the classification boundary for this data set would also be a line, which would be y equal to mx plus c. If we make the model more complicated, what would be the decision boundary for the linear model? Still be a line, still be mx plus c, still the number of parameters would be 2. What would be the decision boundary for k nearest neighbor? It would be some parabolic shape, some part of a parabola. Right? How many parameters typically do you need to define a parabola? More than 2 here, right? So it's a degree curve. Right? It's a higher order degree curve. The number of parameters would be much more than 2, or at least 3. So therefore, or it could be cubic, etc. So what we've seen is that in logistic regression like models, if you add data, the decision boundary or the way to define the decision boundary could still be defined by the same number of parameters, which is 2. Whereas for k nearest neighbors, if we added more data, the decision boundary grew more sophisticated, which could not be described by 2 parameters. It can be described by more number of parameters. Right? So non-parametric does not mean no parameters. Non-parametric means that the number of parameters grow with the increase in dataset size. So if we increase the dataset size from 2 points to some 20, 30 points, we observed that the model, the decision boundary, all of them got more sophisticated, which could be thought of as being modeled by a higher number of parameters. So this is one, first let me go through a few different variants of this before I take your questions, because this is indeed a little bit confusing. Before this, can you tell me any other method which you think is non-parametric, which we've already studied? Okay, let's go over simpler models. Linear regression, is it parametric, non-parametric? Parametric. Decision trees? Parametric, non-parametric? Non-parametric. So sometimes it's easier to think in terms of examples. We have seen one. Okay, first let's go one definition that I have, then we'll go over multiple definitions. Parametric, the number of parameters is fixed with respect to the dataset size. You can increase the dataset, you can reduce the dataset, the number of parameters in the model is fixed. Non-parametric, the number of parameters grows with respect to an increase in dataset. So there, you can expect these models to become more complex when you're given more data. Parametric methods are typically quicker, especially for bigger data sets, whereas non-parametric can take longer to run, and we'll see a few examples why. Parametric often end up making certain assumptions like linearity in linear regression, whereas non-parametric generally don't make a lot of assumptions about the data and distributions, etc. Linear regression is parametric, KNN decision trees are non-parametric. Now let's go over some other definitions. I put these links in the class notebook already. Okay, why don't you look at this definition, try and digest it for a minute, and then we'll discuss. You don't need to understand this line, you can just understand it in English. That should be enough. Okay, assuming you have gone through this definition, given the parameters, future predictions are independent of the observed data D. Can you relate to this in linear regression? In linear regression, you are given a data set D, you learn a parameter linear regression / simple MLPs, you learn the parameter vector theta, then when you want to make a prediction for a test point, do you need anything from the previous data set? No. What do you need? The theta matrix, theta vector, right? So therefore, for linear regression, we can understand that it's a parametric method. Once you have learned the model or the model parameters theta, you can throw away the previously learned data and still make future predictions. For k-nearest neighbors, what happens at the time of training? At the time of training. At the time of training, what happens in k-nearest neighbors? I think someone said the correct answer. Sorry? There is no step in training, right? Or you just memorize the data set. Because for k-nearest neighbor, all you have been doing is pick up a test point, figure out the closest points from the training data, and choose k of them, and then make your predictions. Therefore, in training, you are actually not doing anything. Right? Are you convinced of this fact? In k-nearest neighbor method, of course, there are certain other variants of which where you build indexes at train time, but in the naive version, in the brute force method, we do not do anything at the training time. Therefore, so everything has to be done at the test time, where we look at the distances, pick up the k closest points from the training data, and then take the average or take the majority vote. So therefore, can a prediction be independent of the data for k-nearest neighbor method? No. Right? It's highly dependent on the data. if the data set size increases, and if I have to make a prediction for any particular point, let's say I have to make a prediction for this point, or let's say this point. Right? If I have to make a prediction for this point, now my set of neighbors would change with respect to the earlier example, right? So therefore, what we are saying is that in k-nearest neighbors like method, there is nothing as such you can learn which makes the future predictions independent of the data. Right? So this is one other definition that you can consider. Is this definition making sense? Don't look at all the mathematical details. Just think of it as in parametric methods, you are able to learn certain set of parameters theta, which decouple the future predictions from the past, from the trained data. Whereas for k-nearest neighbors like method, you would still need to have access to the data set in order to make certain kind of predictions. In k-nearest neighbors, during training, can't you consider the decision boundaries? So, okay. So his question is that in decision, in k-nearest neighbors like methods, can you create decision boundaries at the time of training? Answers to that? It is, so exactly. So if you're considering that, it is a very expensive procedure. Like you don't have a very simple method of defining a boundary. So the Voronoi diagram that I showed was defined only for one nearest neighbors. Right? So you'll have to either come up with a very sophisticated algorithm, otherwise you'll have to compute all pairwise distances, which is very expensive. Okay. So Deep is asking a question on what happens if our test point is very far from the training regions, and I would come back to this example. You'd still get a prediction. It may not make sense, but you'll still get a prediction. So these are some sanity checks you as someone who's running the algorithms will need to make. How far is your test data from the training data set? In terms of distributions, in terms of distances, etc. Okay, so we've looked at two definitions. I believe they're making a little more sense now. There are some more defined here. This is also a very nice blog on machine learning mastery. I was trying to... Yeah, I was trying to show a point where it says that there is no clear-cut one definition across these methods. There is this post on cross-validated, which I'll also leave you to consider. And then there is this very nice table from Kevin Murphy's book, which nicely separates out these different classes of algorithm amongst parametric and non-parametric methods. Of course, there are a bit of nuances. There are a few nuances, which we'll skip for now. And another very nice article is this Sebastian Rashka's blog post on the difference between parametric and non-parametric. There will be some corner cases where the definitions get even more fuzzy, especially when we look at models like support vector machines, but we'll skip them for now. Okay. So now we can take some questions on parametric assumption. So this is a very, I would first say that this is an approximation that I'm giving. This is not the exact parameters. What is the set of parameters in k-nearest neighbors? Just the entire data set. So as the data set size increases, the effective number of parameters would also increase. I'm just showing a very crude example as to if you were doing if we were trying to look at the decision boundary as a curve, d degree curve, then we can see that the d degree curve is now a higher order curve. But typically what you want to say is that as the data set increases, my every prediction would now be dependent on all the other data points, which means that my prediction is now dependent on a larger number of data points. Therefore, it's much more, we can say that the number of parameters has increased. Other questions on this? Just one second. There is only a testing phase for this algorithm. Therefore, if I look at this strategy, it's also called a lazy strategy, versus there are other strategies called eager strategies. In lazy strategies, train time, you don't need to spend any time. Whereas in eager strategies like linear regression, you need to spend some learning. You need to do some learning. Therefore, testing can be time consuming because you have not summarized the data into some parameters theta, which you do in linear regression. Okay, how is this a machine learning algorithm? Does anyone wants to answer this question?
So, as I see the application where we can see is that weather forecasting. Let's say that if there is some way in which the observed data can be added to the data set, then it will be very useful.
So consider this spatio-temporal problem. I want to estimate the temperature in one block of a city where I have sensors in the other blocks of the city. Does the dataset have some spatial structure? Because city will have some spatial smoothness in terms of the weather variables and also some temporal behavior. My temperature today would be similar to temperature yesterday, would be similar to temperature one day before yesterday, right? So there is inherently a notion of similarity which exists in the data, which occurs in a lot of strategies. So KNN turns out to be a very, very good baseline. Like it seems very simple, but because of the fact that it's a non-parametric method, it does not require any sophisticated learning strategies per se. It still turns out to be a very good strategy. You also end up using k-nearest neighbors like method a lot. So think of this as you've been thus far creating embeddings, right? So this is one potential application I was thinking of earlier also for something else. So let's say we want to do a facial recognition for this classroom. I just want to take a photo and I want to get the attendance automatically, right? Or I want to see how many people were present during the attendance time but left for a break and then didn't come back. So if we want to do applications like this, I would have to create an embedding for each of you. That's one way to think. So it's so what kind of a problem would you call this? If I want to classify each student, it's a multi-class classification. It's called, so in variants, if the number of students was huge, this would be called an extreme class classification problem, because we have a lot of classes. And typically you'll have only 1 or 2, 3, 4 images per student in your training data set, right? So think of this as if I give you a phone and I tell you to take a few snapshots, you'll probably take 3, 4 snapshots, right? So therefore, these methods are typically trained using something known as triplet loss, Siamese networks, etc. These kinds of specific methods, where you end up with learning and embedding for each individual. Now, for a new individual, or let's say if I want to test who this particular person is, I would take the photo and then I would be able to generate their embedding. I would then just compare their embeddings. Is my embedding closer to Kishan's embedding or is it closer to Jaydev's embedding? Right. And based on my own embedding. So it will then do a k-nearest neighbor search or just the nearest neighbor search and then find out whose embedding looks closest. So k-nearest neighbors does get used a lot in the literature in the community for various kinds of applications. Two we have discussed thus far. Spatio-temporal kinds of methods, as well as for, let's say, image recognition. Movie recommendation that we saw using matrix factorization, you could also plug in k-nearest neighbors there. So we've been discussing this, right? I would like movies which my friends like. So if I can find out that notion of similarity in some vector space, I can then find out which movies I'm likely to. In terms of the memory requirement, because KNN is a lazy method, it needs to store or memorize the entire data. So therefore, if you were to implement this during a training set, during the training phase, you would perhaps just store self.data equal to x comma y, where you just store the data. Let's look at some notebook now to understand this better. Okay, so I've given you some simple data set. I am learning a logistic regression model on this, and a k-nearest neighbor classifier on this, and a decision tree classifier and MLP classifier. So I have 4 classifiers which I am learning on this 2-point data set. Thus far it seems all of them are giving us linear boundaries. Decision tree is giving us slightly different linear boundaries. Why? Why is it not giving me a slanted line? Because decision trees makes axis aligned axis parallel splits. Okay, if we look at the learned functions for logistic regression, it would be x theta or x into w plus b. Decision tree, this is my learned function, right? I'm just saying this is the learned function. This is the learned decision tree. What is the depth of this tree? 1 or 2, depending on how you do the counting. It could have been like this. Maybe just a random choice. Whereas for k-nearest neighbors, you would have something like this. If x1 less than this and x2 less than this, then y equal to 0. If x1 less than this and x2 greater than this, then something else, right? You could model that also as an if-else statement in some sense. Now, if I have a slightly sophisticated data set, and my decision boundaries for these are like this. Right. So my MLP classifier is a simple one, perhaps. That's why I'm getting this kind of a surface. What do you conclude from this? You started with a data set containing 2 points, and you saw the different learned functions. Logistic regression was some x theta or x into w plus b. Decision tree was some decision tree. In this case, it was a 2-depth decision tree. MLP was you do the forward pass, you find out the lodges, the probabilities, etc. For k-nearest neighbor, you can think of k-nearest neighbors as some kind of a if-else statements, right? But not necessarily axis aligned. Now, for a sophisticated data set, the boundaries look like this. What can you conclude in terms of parametric versus non-parametric? What was the value of k? I don't know. Let's see. Let's go back to the code. These are just making number of neighbors is 1. I've just chosen 1 neighbor. What do you conclude in terms of parametric versus non-parametric looking at this? In logistic regression, the decision boundary is still a line. The line, is the line exactly the same as previous, or has it changed? Sorry. We'll not talk about the variance now. So, logistic regression, can you see that previously the decision boundary was a line? Now the decision boundary is a line. KNN, the decision boundary was earlier a line, and now it is. Try and describe this shape. I don't know. Decision tree also, you can see it's a very, very sophisticated shape. Now the learned decision tree is this. Right? So, if you were to think of the decision nodes as the parameters of your decision tree, if you had a simple data set, the parameters you could think as 1 or 2, right? But in this case, perhaps just 1. For a sophisticated data set, the parameters of the decision tree or the way the decision tree is constructed is now much more sophisticated. So therefore, in decision tree, you can see that by adding more data, your model has become much more sophisticated, which is the definition of non-parametric. Logistic regression, that didn't happen. Your decision boundary changed, the value of thetas changed, but it is still the same parametric form. Whereas for KNN also, you will now see something very sophisticated. Right? So I was just showing the different components. Any further questions on this, parametric versus non-parametric? Okay. So Pranav is asking this question that in decision trees, the predictions will depend on the tree that you've learned, right? In some sense, you have been able to condense the entire previous data set into a tree. Does everyone agree with that? In linear regression, logistic regression, we take in the data, we do the training process, we are able to extract out a theta vector. During forward prediction, when we need to do the prediction into the future, we don't really need now any data set D. In k-nearest neighbors, we don't have this. Like we can't feed in a data and learn some parameters theta and then discard the data. Decision trees, he is saying, Pranav is making this argument that it is more similar to linear regression, logistic regression than it is to k-nearest neighbors, right? Does everyone agree on that? And this is exactly the reason why the definitions get a little confusing. Right? As per one definition, if we look at this specific definition, can you say that given the parameters, future predictions are independent of the observed data? For a decision tree, if we stick to this definition, I would say that let's convert it to, given the trained decision tree, future predictions are independent of the observed data? Yes, they are. So it should then be a parametric model if we look at this definition. But if we look at the definition of does the number of parameters increase as the dataset size gets more, then as per that definition, it's non-parametric. So typically it's considered non-parametric. That's why I said that you have to be a little careful about the exact definitions. The simplest definition which is most commonly used is that does the model get more sophisticated? Can it have more parameters as the dataset gets more complex? Good question. In the I'm still unable to get it. Can you speak a little louder? In what example? In k-nearest neighbors. Yeah. I mean, again, it's not exactly that. The definitions are a little fuzzy, right? So you can say that your predictions depend on entire data set, right? So it's a non-parametric method. So you don't really define. So, okay. So because you've asked this question, you can also think of this as non-parametric methods have infinite number of parameters. But let's not go into all of these discussions. Let's just stick to the simple definition. And examples that k-nearest neighbor methods are non-parametric methods, which means that you will require the entire data set at the time of prediction to make the prediction. Whereas for methods like other methods, you're able to, the number of parameters does not grow with the data set size. Any other question? It would be a good exercise to go through these 5, 6, 8 definitions. You search on Stack Overflow, cross-validated, various very nice blogs. And it's not very trivial to come up with something which works across all the examples. This is my understanding, but perhaps we can improve over time. If you can collectively figure out some foolproof definition. Okay, now to the easy part, once we have finished. There are a few important considerations while talking about k-nearest neighbors. What features will you consider? What distance metric will you consider? L1, L2, or Manhattan distance, Euclidean distance? What is the aggregation function? Typically, we use the mean in the case of regression and mode, right? In the case of classification, or majority in the case of classification. What is the number of neighbors you want to take into consideration? What is the computation complexity of the algorithm that you're implementing? So the last one is the most important one for the purposes of this lecture. The others are like more or less settled, or you could just very easily do some search across these. So distance metrics, you can use Euclidean, Hamming distance, Manhattan distance, depending on the kind of data that you have. So if you have numerical data, you'd probably use Euclidean distance. If you have categorical data, what will you use? How do you compare the similarity between two names? You have definitely studied this in your DSA-like courses. Edit distance, some other distance, Hamming distance, some version of these distances, right? How many bits do you need to flip in order to, between two different binary strings that you have? Or if you're given some character strings, what is the edit distance, etc. How many places are the two strings varying? Whereas what application do you think you could use for such, where you need these non-trivial distance measures? what is the difference between the genetic code of coronavirus and a human, or a coronavirus and a chimpanzee, or a chimpanzee and a human? Are they highly varying? Does anyone know this? Human being and the closest primates? Probably not a lot, right? You think? There are a lot of similarity, right? But there is some differences. So can you, let's say if the input features were given to you as these genetic materials, strings of, what are the characters? G, T, A, C, right? A, T, G, C, whatever. So could you then still define similarity between two sequences? For that, you'll have to use some particular method to define the similarity, the number of places at which the characters are different, or something similar. Right? So therefore, similarity is not necessarily restricted to real domains, but you'll have to be very careful, and you'll have to also incorporate the domain expertise. Manhattan distance versus Euclidean distance. Why is it called Manhattan distance? So a lot of cities like Manhattan have these crosses and I don't know what is the other thing called. Avenues, crosses and avenues. So basically these rectangular grids. So if you have to reach, or it's also called taxi cab distance, if you have to reach from one point to the other, you can not go via the green line, right? But you can go via the yellow line, via the blue line, via the red line. This is a fun question, I think, typically asked in a discrete maths kind of a course. What are the number of ways in which you can reach from point A to point B? Some of you might have been asked this question in your master's interview also. How do we choose the correct value of k? K is a dash hyperparameter. How do we choose k? Via cross validation. Low value of k leads to high variance. So each point has a very high influence on the final output. Therefore, noise can also influence highly. The other way to think about it is high variance. We saw that if we modify the data set even a little bit, your final predictions will change very significantly. That's another definition of variance. High value of k will lead to very averaging out effect, which means very smoother decision boundaries, which means that your predictions even on the training data set will not be very good. So if we take this specific example, for k equal to 1 classification, what is the training accuracy? 100%. K equal to 3, what is the training accuracy? How many points would be classified correctly? 4 by 5. So k equal to 3 is having higher train error or lower training accuracy, which is also showing you another proof of the fact that as you increase k, the bias will increase. Some examples here. If this is the data set k equal to 1, you see very high variance. You can actually see that there are these regions, which should perhaps have been blue, but because of these 1 or 2 brown points, they are colored in brown. With k equal to 3, this seems like a good fit. K equal to 9, you will have very high bias, which means that there will be some very important regions which you will end up missing. Aggregation I discussed, you could do median, mean, mode, etc. Any kind of aggregation, depending on the classification versus regression problem. Okay, now we come to the most difficult algorithm in the course, the KNN algorithm. The algorithm is you keep the entire data set for any query vector q. What should be the dimension of q? Should it be the same as any point x or any point y? Any point x. You find the k closest data points and their x stars and correspondingly predict y star as the mean of this. That's just a 2-3 liner. Of course, because it's very simple, there are a lot of other nuances which we need to consider. How exactly do you find out the k closest data points? You find out the k closest points by finding out, let's say if you've picked up the distance metric, but how do you find out that? And then you make the final prediction. Okay, so we still have 15 minutes. I will try and cover the curse of dimensionality. Before talking about this, so let's consider a prediction problem where I have, so similar to the problems we've been discussing earlier, I want to predict the energy consumption of this room, of this campus, etc. I have taken some very obvious features, which is the number of students, the baseline load, etc. Now someone tells me that let's keep adding more features so that will improve the model. Some more features might be, let's say, the number of gardeners in the campus, because someone might say that is proportional to the amount of horticulture requirement, which is proportional to the amount of water, which is proportional to the amount of electricity, something. Some other features you could add. Would adding more features always help you or no? Why should it not help you? Let's say it is still important. Let's say if the feature is okay. So let's say if the feature is not particularly important, perhaps the coefficient for that should be just 0. Right? So by that argument, does it make sense that if we increase the number of features, our model should always do better? It should not go worse. Then we should always try and add more data. But the next slide says curse of dimensionality. So there is some curse, some problem that we face if we increase the dimensionality of the data. It's very apparent in k-nearest neighbors-like methods.
Can it be that for the extra parameter that we add, the number of outliers would also increase?
Okay, so Deep says that the number of outliers would also increase. Okay. Yeah, so this one I'll say is in a more generic sense, and then we'll come on to the specific example. So the curse of dimensionality says that with an increase in the number of dimensions, the distance between points starts to increase. Looks like a very vague statement at this point of time. Let's go through some code and try and understand this.
Sir, we have learned that if we increase the dimensions, anything goes on.
Yeah.
So is it that
It's similar to. So those who have taken the data science course would perhaps have already studied this. But let's perhaps take a different view of the same problem, even if you've studied this earlier. I have uniformly generated 10 points from between 0 and 1. And I've plotted this, I'm on the scale. So this red points become my training data set or my train points. I pick up a test point at random. Again in this range 0 to 1, test/query point. And I've then marking my closest and the farthest data points. So the green one is the closest training data point to my test point, and the yellow one is the farthest training point to my test point. Can you see that the farthest point is very, very far compared to the nearest point? Perhaps we just got lucky here. So let's run it for another iteration, another different random seed. Again, the farthest point is very far compared to the closest point. Let's run again. Again, the farthest point is very far. Maybe not as much as the previous two cases, but the farthest point is significantly far compared to the closest point, to the test point. Now I will repeat this experiment multiple number of times. And I am plotting the ratios of the distance to the closest train point versus the distance to the farthest data point. Distance to the closest data point is a very small number. Distance to the farthest data point is a large number. If I do this experiment multiple number of times, I'll get these values 0.01, 0.01, 0.04, 0.05, so on and so forth. I create a histogram out of that and I plot that. It seems that it's very heavily skewed towards 0, which means that for this one-dimensional problem, most of the test points have a very, very close training data point and a very far training data point. Right? Does this make sense? Now we will do the same experiment for the same number of points, which was 10, but in 2 dimensions. So now we have 10 points in a 2D space. I will do the exact same experiment. And now this is my test point. My closest train point is this orange one, oh sorry, this green one, and my farthest train point is this yellow one. Now what can you say about the ratio of the nearest to the farthest data point? Has it increased with respect to 1D, or has it decreased? It has increased. I repeat the same experiment multiple number of times, and the histogram clearly reveals this. The ratio of the closest to the farthest data point has now on average increased as I've increased the data set size. Importantly, I've kept the same number of points, 10 in my data set. Now I can't plot it, but I'm now doing the same experiment for varying number of dimensions from 1 to 20. Sorry, 1 to 101. So I'm looking at, 1 to 100. I'm looking till 100 dimension data sets, but I have still just 10 data points. Okay, what do you now observe? As you increase the dimensionality of the data set, the ratio of distances, which is the distances between the closest point and the farthest data point, will increase or decrease? Increase or decrease? What can you observe from this plot? It is increasing. So what can you conclude from this? As you increase the dimensionality of the data, what happens? For any query point, the farthest and the closest data point are very close. Or in other words, in very high dimensional space, all the points are very far from each other. And if that is the case, does k nearest neighbor have any significance, have any meaning? You were trying to find out k closest neighbors. But if each of the point is so far from the other points, then you don't have any notion of closeness. Right? Each of the point is on the outer edges of that high dimensional space. So then, can someone now tell me why was this term called the curse of dimensionality? As you increase the dimensionality of the data, the average distance between points has increased, the distance between the closest and the farthest points has increased, which also means that the notion of distances, which we had nice intuitions in lower dimensions, is just become useless. If I were to increase this to further number of dimensions, the ratio of distances would probably be close to 1, which means that my farthest point and the closest point are equally far. Right? How can we mitigate this? Or if we go back, let's look at another view of this problem. In 1D space, the gaps that you're observing are on average, let's say 0.1 units. Right? You have 10 points in a from 0 to 1 range, the gaps are approximately 0.1. In 2D space, the gaps have increased. Right? If you were to fill up this space, what do you need to do? Maintaining the same density. What do we need to do? In 1D space, if you needed a density of spacing of 0.1, you could get away with 10 points. In a 2D space, if you use 10 points, the density is much lower. So if you want to maintain the similar level of density, what do you need to do? Have more data points. If you move to 3-dimensional space, you need 10 to the power 3 data points. So therefore, if you want to have higher number of dimensions, in order to maintain that notions of distances, you will have to have dash number of points. Dash more number of points. Exponentially more number of points. Now, is that a problem? Whenever you increase the dimension of the data, you'll have to have much more number of data points to maintain the notion of distances, which is extremely hard to get. You can't suddenly get exponentially more data. Therefore, we have to be very careful with respect to the dataset size, especially for problems like k nearest neighbors, where the distances are defined, where the distances are the main factors which decide the classification of the regression. Next, I'll show that for 1 dimensional, I'm using 10 points. For 2 dimension, 50 points, 3 dimension, 200 points, 4 dimension, 2000 points. I'm not exactly doing exponential, but something to that effect. And if I do that, and then if I look at the distances between the nearest and the farthest points, can you see that they're almost all same? So what do you conclude from this graph? if you want to maintain a notion of density or a notion of equal distances between nearest and farthest points across varying dimension, you need more data points, generally exponentially more data points as you increase the dimension, which is why this is known as a curve. So you can plot multiple such distances to multiple such metrics to try and understand this. Okay, I think this is a good point to end today's lecture. We'll see based on the time we have whether we should study approximate nearest neighbors, or I can just leave it up to you and give you some references to that. Next we'll meet after the whatever break you have, what to call it.